Okay. Okay, good. So just let's recap. Given two distributions, this is the trade-off that we have. Any threshold corresponds to a point on the ROC plane and to splitting the regime to the blue area and the red area. Okay, of course, different distributions will lead to conceptually different trade-off functions or ROC curves. So notice what happens here. If I chose this point, so anything below, what are the two distributions here? As you can see, these are two uniform distributions. One of them is between 0 and 3, and one of them is between 1 and 4. Okay? So if I chose a point below 0, and I said anything to the right is red, and anything to the right is blue, and anything to the red is left. What happens here? What do I get? Is there what will I guess for the blue distributions?
You will get only true positive. Like
you put the threshold there.
Yes.
So you get for the blue only one in the true positive, and one in the false positive.
Why? Because what will I guess? I will always guess positive. Right? Notice, I say that anything above minus something, I will guess positive. Those distributions are supported only on the positive regime. So obviously I'll always guess positive. And indeed, you may not notice it there, but there's the point at that corner, 1, 1. Okay, now let's say I move to this area. Now I have a point where I'm already within the range of the red distribution, but not within the range of the blue distribution. So in other words, if I sample from the blue distribution, what will I guess?
True.
I will always, not true, positive you mean, right? That's confusing. I would always guess positive. But when I sample from the red distribution, sometimes I will guess negative with some probability. And as you see, I'm starting to decrease my false positive rate without harming at all my true positive rate. And this continues until I get to this point, 1. At this point I'm here in this corner. I managed to decrease my true positive rate by my false positive rate by some quantity, and didn't harm at all my true positive rate. Once I continue, now this is linear, right? Anything I gain with the true positive, I lose with the false positive, right? Because there's no better hint here or here or here, right?
Is it affine actually because it's not on 0?
Sorry?
Isn't it affine, not linear?
What is affine?
Affine, okay. Linear plus a constant.
Yes.
Affine.
You're asking is the plot? The plot is
It's not
yeah.
linear, it's affine. How do you pronounce it?
Affine, I think you pronounce. No, but I'm not sure I understand what the question is. You're asking, like, is the trade-off function or the ROC curve affine in this case?
Yeah.
Yes.
No, you said linear, it's fine, yeah.
No. I'm saying linear is not necessarily linear space. Linear is literally linear.
Okay.
So the line here, this is a linear section of the trade-off function.
Yeah, okay.
And then, of course, when I get to the other, and now at this point I guess false. I guess negative for all red points. So my false positive rate became 0, and yet I have some true positive rate which gradually decreases. Okay? This is another option. Okay. Now notice that in both examples that I gave so far, the yellow point moved across the green ROC curve. Now reminding you, the ROC curve identified what is the best, highest true positive rate we can get for any finite false positive rate. There was nothing a priori that required that the point for any specific decision rule we will make will be on this line. It could have been below it. So by going through the whole range, the entire range of possibilities for this decision rule, for this whole family, and always finding a point that's exactly on the line, this effectively tells me that this decision rule family is optimal. Right? Because had I chose some other rule that, like, I don't know, anything above 4 and below -2 is blue and anything in between is red or something like that, I would get a different point, and that point might have not been on the curve. It might have been somewhere below it. It won't be above it, right? That is the definition of the curve. But it might have been below it. But as it seems, in both of these examples, the threshold decision rule is the optimal one. How would we know that it's optimal? And more importantly, how can we identify in the general case what is the optimal rule? So there's a lemma called Neyman-Pearson lemma, and that is one of the most important and essential properties of the entire hypothesis testing perspective, which states the following thing. For any point, for any value, not point, any output of the distributions, I can ask what is the probability of observing this point under distribution 1 and under distribution 2, right? If it's continuous distribution, so it's not what the probability is, but what is the probability density function. But for now, let's be typical computer scientists and ignore the fact that measure theory is a thing. So any point, any output, has some probability under this distribution, some probability under that distribution, and I can sort all the outputs by the ratio or the log ratio of these two distributions. Right? So I would say a point with a larger ratio intuitively is more likely to be from the one in the numerator. Point with the smaller ratio more likely to be from the distribution with the denominator. So Neyman-Pearson says the following thing. Take all of your outcomes. For each one, compute the log probability ratio. I mean, log is a monotone function, so it's the same. But we typically prefer the log probability ratio because then it maps to the entire real. Any point maps to the reals, including plus and minus infinity, maybe, but, right? Because if there's a point that has 0 probability under one and some finite probability under the other, then the ratio is infinity. But still, I can go through the entire line of reals plus minus infinity, and just map all of the outcomes to this line. Neyman-Pearson tells me that if I define a threshold on that line, not in the regime of outputs. The regime of outputs is people, is big images, is something arbitrary. But like I observed a image that came out of a model, and I'm trying to guess what is the probability that it came out of the fusion model versus what is the probability that it came out of, I don't know, Soho. It's not like just any pair of distributions. Well, there's some probability under this, under that. Take the ratio, take the log, I put it somewhere on the line. Put a threshold. This is always optimal. I'm somewhat ignoring the fact that there's a subtlety that if there's probability atoms, then you might not correspond to any values, so you need to flip a coin. Whatever. If everything is continuous, life is nice. So now you might think that I'm showing you again the same plot as before, but no. Look at the x-axis. 2 slides ago, I was showing the value of the threshold. So these were different values of the possible threshold, and each one of them induced both this split on the between the 2 distributions and a point on the ROC curve. Now I'm showing you something different. For any point on the slider, this corresponds to a x-axis value on the ROC curve. It's not I chose a threshold. It's I chose what is the false positive rate that I want. And the coloring in the left plot is the result of this threshold. It's like if I want to have false positive rate of 0.1, which points on the line I would guess yes, and which points on the line I would guess no? Well, it just so happens to be all the points that are to the right of some value. And why is that? So I will not formally state this claim, but I will explain it intuitively, and I think that suffices for our purposes. If the log probability ratio between the 2 distributions is monotone in the value, in the case of a one-dimensional distribution, then a threshold on the values, of course, corresponds to a threshold on the log probability ratio. And since the threshold on the log probability ratio is the optimal, the threshold on the value is also optimal. So, for example, when you have 2 distributions, not any 2 distributions, imagine if I have like bimodal distributions and whatever, then even if it's the same distribution shifted, the log probability ratio might no longer be monotone. And furthermore, you'll see in the assignment, even 2 very clean unimodal distributions, very natural ones, still might lead to non-monotone ones. They're not the same the same family, or they are the same family but different variants, or all sorts of stuff. So you can't, like, the conditions for which this will be the case are very specific. But had you managed to prove that the log probability ratio is monotone in the value of the function of the outcome, then you know that the threshold and the value corresponds to a optimal decision rule. Okay, by saying optimal, I mean a point on the curve. Again, between the points on the curve, there is no hierarchy. That's a matter of taste, in a way. Okay. So now let's go back to the assignment. Let's do this. So we have 2 binomials. And we want to find the optimal decision rule and all the options. So, for each of the... Wait, how many outputs does a binomial with these parameters have? 6, right? 0 and the 5 outs. Okay. Each one of them has some probability under 1 and under 2. P and Q here, I don't know, again, choose, because it's symmetric, so choose one of them to be the top one. Let's say, for simplicity, H1 is the top one, is the P. So we compute the probability ratio and then the log probability ratio for each of the 5. And then, well, the question may have not been phrased properly. There are many possible decision rules. I mean, what are the possible optimal decision rules? What are the possible decision rules over that correspond to how do you call it, to the trade-off curve, to the ROC curve, and then let's compute the false positive and true positive and draw it. Okay. Give you a few minutes and let's try to fill the values. It's a good exercise. Just feel it in our hands. Yeah, I don't care for the, how do you call it? Decimal representation. If it's log, a third, whatever, that's good enough. Like,
So H0 is negative.
H0 is, yeah. Let's say H0 is negative, and when we consider the ratio, it's going to be the ratio of positive over negative.
Okay.
So let's just do it. So there's log of H1 of 0 over H not of 0, and so on for 1. Okay, so let's start filling up things together. Nice. So let's see, how can we do this? What is H1 of 0? Or actually, what is H1 of I?
It's actually easier to calculate the division sometimes.
Oh, exactly, but that's what I want to get to. What is H1 of I?
That's the probability of.
No, not what it means. What is it exactly? What is the expression? The probability of getting I under H1.
Well, that's I to the power of.
Wait, first we have the binomial coefficient, right? There's 5 choose I.
Times 0.25 to the power of I times
1 minus that, which just happens to be
0.75 to the power of 5 minus I.
right. So, and when it comes to H naught, the binomial coefficient is the same. The only difference is the how do you put the powers. So we would have here log of. So we'll have 0.25 to the power of 0 times 0.75 to the power of 5 over 0.5 to the power of 0 times 0.5 to the power of 5. Or we can actually take the ratio. So this ratio is a half, right? So in a way what we have here is, here we have 2 to the power of 0. And here we have, this is 3 over 2, right? To the power of, this is 3 over 2 to the power of 5. fine. In fact, because the numerator would always have the 2, so it's even simpler. There's always in the denominator the 2 to the power of 5, regardless of what is I. So the only one is that the numerator has 3 to the power of n minus I. Okay, so this is very convenient. So we have 5 minus 0. Sorry. Will it wake up? Good. This is 5 minus 0 times log 2. Sorry, so log 3 minus 5 times log 2. Fair enough? I just did the fact that 3 to the power. So, okay, you know what? Let's do it step by step. Let's do it step by step. So, log h1 of I over h naught of I is choose 5I times 0.25 to the power of I times 1 minus that. So it's 0.75 to the power of 5 minus I, and then over, so it's the same. So this is log. This is the same 5 choose I, which will cancel. Here we have 0.5 to the power of I. Here we have 0.5 to the power of 5 minus I. Okay? So here we have, I think no. Okay. So 0.25 over 0.5 is a half. Okay? So we have a half to the power of I. 0.75 over 2.5 is 3 halves. So it's times 3 halves to the power of 5 minus I. Okay? So the numerator has the 3 and then times 5 minus I, and the denominator has 5 times, regardless. It's just, okay. So now I use all the log rules to have 5 minus I times log 3 minus, right, 5 log 2. Okay? Now, this is algebra. What matters is the following thing. How does this behave as a function of I? This is a monotonically decreasing function as a function of I, right? Because this is a constant, and this, the 5 times log 3 is also a constant. So we just have basically 5 times log 3 over 2, which is whatever, some number, minus I times log 3. So it's a linear function. So what will be the thresholds that we would consider for the optimal, the ROC curve? Again, thresholds on the number I, because we fulfill the property that we needed, that the log probability ratio is monotone in I. Okay? So let's just draw it. So now we're considering 6 points exactly, right? 7 points now. There's 6 possible values, so there's 7 ways we can split them. We can say either all of them are I guess 1, all of them I guess 0, or any threshold in between. Okay, so let's fill the 2 ones that we don't need to think. If for all of them I guess 1, what point does it correspond to in this curve? 1, 1, right? This is putting the threshold at, let's call it 6.5, right? Like, sorry, 5.5, above 5. So as there is, consequently, all of them are defined to be, 5.5 is just a way to say like above 5. And what is the other one that we have easily? Bottom one. This one corresponds to what threshold?
-1.
Yeah, let's say, how do you call it? Let's do half, so it's going to be natural. And then we'll have a bunch of points that will correspond to what?
0.5, 1.5, 2.5, 3.5.
Exactly.
4.5.
So, come on. Oh, I think I need to connect it. Right. So I don't know if, what? 1, 2, 3, 4, 5, 6. Yes, this is one too many. I don't know. Let's steal this one. Okay, so let's just compute one of them. So we have the. So let's take this one. This one corresponds to what?
1.5.
1.5, meaning putting the threshold between 1 and 2. So 0 and 1, we would guess H1, H0, and 2 and more, we would guess the other way around. We would guess H1, and the ones above, we will guess H0. Right? Okay, so let's call it 1.5. So what is this point? What is the x-axis? It's the probability under what? The x-axis corresponds to, sorry? H0, right? The negative distribution of what event? Of getting which values?
Positive.
But which values concretely now that I chose a particular point? This is the threshold.
Above 1.5.
Why above? In this case, larger.
Okay.
Right, because now the H1 has a smaller expected value. Okay, so this is basically P. Let's put here. This is P of 0 given 0.5 plus P of 1 given 0.5. When I mean given, it's like given that this is, and this one. What is the y-axis?
The probability that we guessed true, and it is true that we guessed that we're in the 0.25, and it is in 0.25.
Right. So what will I change from this right up? Will I change which guesses or which conditions?
The condition.
I want to make sure everyone is okay with it. What is the difference between the x-axis and the y-axis? Not what did I guess, but under what distribution did I guess it? So this is again the probability that I will guess 0, but now under the 2.5 option plus the probability that I would guess 1 under this option.
The probability that you'll get 0, the probability that you'll get 1, not that you'll guess.
Right, sorry, yes, that I will get 0 or get 1 because that's what will make me guess this option. Okay, and again, these are two numbers, doesn't matter what they are. Okay, so now we had a hands-on, and it also helps to somewhat understand like what are the different quantities that we have here. I have here a whole bunch of quantities that are the probability of the event under two distribution, and then the event itself is basically defined by the threshold on the ratio of those same probabilities, which is a somewhat confusing concept, which is why this is not the easiest thing to understand, but still, it's well defined, and it is much more intuitive even in a way than the math says.
But what is somewhat confusing is the fact that the smaller distribution is the second.
Yeah, but that's just a poor choice of parameters on my hand. I should have chosen 0.75, but yeah, I agree. This is the same as if in some of these plots I would choose H1 to be the one with the smaller mean.
Yeah, it's the same. Maybe instead of using H0 and H1 positive, like HP, HN.
So
Doing the language of positives and negatives, it's
I
easier to
agree.
make them.
The problem is that the privacy literature, even though it's in the computer science realm, got most of its terminology from hypothesis testing for some historical reasons. And on the other hand, people are used to binary classification. So I tried to combine them to sort of help everyone remember that these are just two equivalent perspectives. And I agree that it also has some downsides. So we'll discuss it later. Okay. So bottom line, we now have a clear definition. We put a threshold on the log probability ratio, which in some cases very conveniently translates to a threshold on the actual values. And this defines a point on the optimal Pareto frontier, the ROC curve. Okay, now let's go back to privacy. So, first of all, let's map it just to the language we had before. In the context of privacy, what are the two distributions and what does the decision rule correspond to?
Stuff with the new data, the stuff without the new data. That's the curves.
Not the curve. So the distributions correspond to what are the possible outcomes and what is the probability of the possible outcomes under the two worlds we're considering. Again, reminding you, we took the worst case perspective. So we said the adversary knows practically everything. The adversary knows practically everything, and there's only one piece of information that they're lacking, which is it me or you, or am I there or not? So in that world, they have exactly two options of what's going on. Furthermore, they know how the mechanism operates, so they know what is the probability of each outcome given that this is a data set or that is a data set. So they have two distributions. And given an outcome, they're trying to guess. And a problem for us will be if they're very good at guessing, and a success in maintaining privacy would be if they're
Very bad at guessing.
what is very bad, about random. Okay, so can we say something like, well, a mechanism is private if the adversary's success rate will be very low or very high? No, I can't say that. Why? Because there might be a prior over the two possible worlds. So imagine it's the let's say it's Google has, I don't know, 1 billion users, and they run some experiment over 1,000 users out of those billion users. And now the adversary needs to guess whether a particular user was in the data set or not. And the adversary will guess, no, he was not, and they will be correct 99.99 whatever percentage of the time, and you'll be like, whoa, this is not private. I mean, the adversary managed to guess correctly nearly always. No, that's no big deal, because this is the probability that they will guess it regardless of if the element was in the data set or not. On the other hand, if it's a census and they survey practically every person in the United States, then you can give or take guess one with very low risk. So again, like in the case of binary classification or trade-off function, this is a trade-off. We need to have something more nuanced and say, well, for any level of false positive rate from the perspective of the adversary. False positive in this case will be, for example, that the adversary guesses that you were in the data set, well, when in fact you were not. So an adversary that can guarantee that they would not guess incorrectly that you were in the data set with probability greater than 0.01, what is the probability that it will guess correctly that you were in the data set when it is the truth? So, the further the trade-off function is from the diagonal, the better their guess is. So, the better their chances to succeed, the worse the privacy, the more information leaked. The closer the trade-off function of the adversary is to the diagonal, the closer his guess is to a random guess. Now, reminding you, the trade-off function is not a function of the decision rule. It's only a function of the distributions. Right? So, the moment I define the two distributions, I define the ROC curve, the trade-off function. And what defines these two distributions? The choice of the mechanism. So a mechanism defines a trade-off function that tells me what is the worst thing that an adversary can do, even had they known everything. Okay? So, a lot of text, but the idea is very simple. A natural way to define privacy in a way that captures the best protection we can guarantee is to say a mechanism is private if the induced ROC curve for any element in any data sets is relatively close to the diagonal. So the only thing left to define is how do we quantify relatively close, right? Because there are many plots that I can draw that will be, some of them will go up further at the beginning, but then will plateau. For example, think about these two. Can you tell me which of these trade-off functions is better? I don't know. One of them at the peak is worse. One of them in the middle is worse. There's no clear hierarchy unless you have, in this case, there's a clear hierarchy. Because, of course, which one is the most private here? The purple. Oh, right. Sorry. And then this one, this one, this one, right? But if I had one that is, I don't know, let's say that looks like this. Right? So now it is maybe less private than the purple one, the one that's closest, but now when I want to compare to the green one, well, that's not well defined. In some cases it's better, in some cases it's worse. So you need to have some measure of closeness of a trade-off function to the diagonal in order to define privacy. And here's a proposal, probably the most natural one, just a single line. A linear bound, right? And it's not going to be a single line because everything is sort of symmetric, so it's going to be two lines. Okay. So what do I mean? This is the trade-off, the red line, and here's what I can do. I can control the angle of the line, and I control its shift, its intersection, right? So these are two parameters. Again, I chose the log just so it's not too sensitive, right? So if I chose the log to be, it doesn't have the number here, but whatever the number here is, and whatever the shift here is, okay. So log of the slope is 0.73, log of the shift is 0.9, and if this is the requirement that I gave, then is this ROC private or not? It's sufficiently private or not?
Seems not.
Why is it not?
Oh, the privacy panel, the ROC is the same.
The ROC is the red one.
Oh.
The blue line is what I require. So is the ROC closer to the diagonal than the requirements or further away?
It's closer. No points.
It's below, right? So that it means that it's sufficiently private. But if I move the shift, let's say this way, then we have a problem because at least part of it is not below. So it means for an adversary that will choose a fixed, let's say, 0.1 false positive rate, that adversary will be able to do better than this blue threshold. And the same, I can increase the shift but decrease the slope, and again I'll have a problem here. Okay? So this is a relatively natural privacy notion.
But you will still have the same problem as before. When you have two books, and then you can't say that one of them is better than
No,
the other.
I'm not asking if one is better than the other. I'm just saying if one bounds the other. So the blue line doesn't say this is the best one. It just says
Okay.
if you want to be private with these two parameters, right? Like basically now I have a privacy notion that is parameterized by two numbers. The slope, or its log, and the shift. And I say you are slope comma shift private if the ROC induced by a mechanism in any neighboring data sets is below this these lines. Okay. So there's only one last thing to show, and that is that I can move my okay. So yeah, okay. So is this an okay? So let's go maybe step back. Do you have any second thoughts about this definition? Like, is there something that is superficial here? Is there something that is arbitrary? Is there something here that we could have chosen differently once we committed to that decision at the very beginning? That is that we want to protect against the worst case analyst. Once we did that, could have we chosen any other path leading to this point?
You should see the next slide somewhat.
That still doesn't answer the question. But
I guess, what does it mean a slope and a shift in the real world? That's the...
so you say, what is the interpretation of this?
Yeah.
Okay. So let's think about it. A shift is maybe easier to define. A shift means that being very, very close to... So imagine I have like very few events, very low probability events under one distribution that are impossible under the other one. Like there's some... Had I participated in the data set, then there's some negligible probability that this outcome will come out. And had I not participated, it would have been impossible. But the probability is 1 in 10 trillion. So the ratio is infinity. Which feels like it doesn't capture a real phenomenon. So the shift says, in a way, I don't care for any false positive rate, or again, the flip side is false negative rate, that is so small that it's like completely negligible. That is what it says. And then it says that from now on I require like basically a constant trade-off between false positive rate and true positive and true positive rate and false positive rate that might be a little better than just 1-to-1. Like, you're slightly more likely, but again, like, this was a diagonal, this is another linear, this is another line. It's just with a slightly different slope. This is the definition. So, maybe let's split it into two things. Is there a choice other than bounding in some way the ROC curve? And is there a choice for this bound to be expressed in any other way but basically a combination of two lines? Like, once it's a straight line, then it must be parameterized by these two numbers. So I would not claim that the line is necessarily the only thing possible. It's just like a natural quantity. But yes, you can have, a parabola, you can have whatever. But what I will claim is that the choice of defining privacy as an upper bound on the ROC curve is inevitable. Because you can't have a single point, because that depends on the context and how much information we know, whether this data set is more likely than that data set or not. So each one of them corresponds to a different world. So all we can say is that you cannot be further away from the diagonal by too much. And it just so happens to be that this is exactly the definition of differential privacy, just choosing the straight line definition. So, bounding the true positive rate by the linear function of the false positive rate, which has some slope and some intersection, is exactly the definition of privacy, where it's epsilon is the log of the slope and the intersection is the delta. So, in other words, here we see a few mechanisms. Doesn't matter what they are. But each one of them, I can tell you, is a noise addition mechanism. Maybe we will figure out together what is what. And here we can control the privacy and the parameters. So, let's start with putting the shift at 0. What family of privacy notions does it correspond to? Or what type of privacy definition does it correspond to?
0, 0.
No, sorry. Just keeping this at 0 and this I will change. So, what kind of privacy is this?
Delta. Is it one parameter?
It has a name. This is pure DP, right? This is the pure DP family. Okay. Is the orange line pure DP for any parameter epsilon?
Which line?
The top one.
No.
Sorry. No, right? Regardless, except for infinity, whatever, but right? Like anything below infinity, it can't be. What about the red one, this one?
Gotta scroll down to see.
Sorry?
Gotta scroll down so you can see.
You can look there, everything is symmetric.
Oh, yes.
So you can't tell because it's a matter of resolution. Right? It might be that because that depends on what exactly is the angle of that curve. Like basically, what is its derivative at 0 or at 1? Right? If it's flat, you're okay. If it's and the green one, this one seems like you can have a linear line. Notice this looks linear for a while and then it just has a small curve. Okay. Any guess which family of noise does each of these curves correspond to?
I would assume the green one is the plus and the orange one is Gaussian.
Orange is Gaussian?
Yes.
Why? Yeah, based on.
Okay. Thing is, first of all, Laplace is definitely DP, and green is DP.
Okay, so visually,
Epsilon.
the green one is basically it has like this perfect slope. Like had there been a mechanism that would have a trade-off function that is exactly the blue line, the bound that we're controlling, okay? What will its privacy be? Exactly epsilon comma 0 dp for some epsilon, okay? This one has epsilon throughout, except for like some small regime in the middle where it's even slightly better. This is indeed typical of Laplace mechanism, because Laplace noise basically has some probability of being the privacy loss, log probability ratio, has some probability of being plus or minus epsilon, but also has some probability of being between plus and minus epsilon. This one has some probability of leaking all the information and some probability of being sort of constant. Which type of distribution would have this property? We saw it before.
The exponential mechanism.
No, exponential mechanism will never have privacy.
Well, it could have the delta. We have a big
Exponential mechanism doesn't have. Exponential mechanism is pure DP.
Okay. Well, I mean, okay. Remember the exponential mechanism is Laplace but absolute value.
Oh, the exponential distribution.
Yes.
That
because it starts at 0.7 around, it's not exponential distribution.
It's not that, because the exponential distribution, at least in one side, will have privacy loss that is epsilon. And the other side, it can go crazy, but in one side, it's going to be epsilon. And here, it never has a constant slope starting from 0. This is the uniform. Because the uniform, when you are in that regime where they both have the same probability, has this straight line. And in the other regimes, it's only one of them. We can see it here. We saw it before.
Yeah.
It's this one. And the third one is the Gaussian. And the Gaussian, even though we can't see it here in the image, it is not pure DP. And why is that? It's because the derivative at 0 and at 1 is 0 or infinity, which means there is no slope that it's below it. Okay, so bottom line, what we saw in this lecture is that if we take the worst case perspective, which corresponds to the strongest adversary, the formalism that corresponds to this is what is called membership inference attack. Right? I want to know if a certain element was in the data set. And because we assume the strongest adversary, this boils down to a binary classification. They don't have any other part they need to consider. Binary classification is quantified by an ROC curve. Similarly, hypothesis testing, they call it a trade-off function. And the optimal decision rule is a function of the log probability ratio. And it's in fact a threshold in the log probability ratio. So differential privacy, which says all of I want to know what is the probability of the event that the ratio will be below something or above something, is effectively an upper bound on this ROC curve. So from now on, when we will use differential privacy, we can use it with the perspective of how hard it is to the most powerful attacker to figure out by observing the output if a certain element was in the input. And when we say how hard it is, it means how much better than a random guess will its prediction be for any possible neighboring data sets. Okay? Thank you.